Good morning viewers. Today in applied physics we will learn about semiconductor transistors. So in this we will study about the history of BJT, means bipolar junction transistor, how first BJT, that is bipolar junction transistor, came into being, what are the basic symbols and features. Then we will study a little bit of physics on semiconductors, how currents flow in transistors, basic configurations, characteristics of transistors, and finally applications in which we will study about transistor as an amplifier and a switch. The history goes back to 1947. Before transistors were invented, circuits used vacuum tubes. These vacuum tubes were very heavy, that is large in size, fragile, and they generated a large quantity of heat. Moreover, they required a large amount of power. The first transistors were created at Bell Telephone Laboratories in 1947. William Shockley, John Bardeen, and Walter Brattain created the transistors in an effort to develop a technology that would overcome the problems of the tubes. The word transistor is a combination of the terms transconductance and variable resistor. Today, the advanced microprocessors that you use, they can have as many as 1.7 billion transistors. So, what is a transistor then? It is a 3-terminal electronic device made of a semiconductor material. Transistors have many uses like amplification, switching, voltage regulation and modulation of signals, then oscillators, and the picture that you see, these are some of the transistors that are being used. First BJT, this is the picture of the first bipolar junction transistor that was constructed. Basically, the transistor was the most important invention of the 20th century, and the story behind the invention is one of clashing egos and top secret research. The picture shows the workbench of John Bardeen and Walter Brattain at Bell Laboratories. They were supposed to be doing fundamental research about crystal surfaces. The experimental results hadn't been very good, though, and there is a rumor that their boss William Shockley came near to cancelling the project. But in 1947, working alone, they switched to using tremendously pure materials. It dawned on them that they could build the circuit in the picture. It was a working amplifier. John and Walter submitted a patent for the first working point contact transistor. The three shared a Nobel Prize in 1955. Bardeen and Brattain continued the research. Shockley quit to start a semiconductor company in Palo Alto. It folded, but its staff went on to invent the integrated circuit, that is the chip, and found what you today know as Intel Corporation. By 1960, all important computers used transistors for logic and ferrite cores for the memories. So, this is the picture of Bardeen, Shockley and Brattain. They built the first point contact transistor. This is the schematic diagram of the first point contact transistor. This was the semiconductor here. Then there was a gap between emitter and the collector. This is the collector. So, in the picture, this is the original one, this is the emitter here. Then there is a spring here, a collector and the base. So, a gold foil was glued to a triangular insulating wedge. A narrow gap was cut with a razor blade to form the emitter and the collector. The gap was approximately 50 micrometer wide. Under forward bias of the emission base junction, minority carriers are injected into the base. Most minority carriers are collected by the reverse biased base collector junction. Thus, the base controls the current flow between emitter and the collector. The point contact transistor is a surface effect device, that is, important effects occur at the semiconductor surface, and surfaces are easily contaminated. This is again the picture of first bipolar junction transistor. So, there was one end which was called emitter, other was called collector, and the narrow region in between was called the base. Now, let us study something about conductors, insulators and semiconductors first. The conductors are those materials in which the flow of electricity is governed by motion of free electrons, like for example metals. In the case of insulators, flow of electricity is governed by motion of ions that break free. In conductors, as temperature increases, conductivity decreases due to more lattice atom collisions of electrons. In case of insulators, as temperature increases, conductivity too increases due to lattice vibrations breaking free ions. From conductors, you get the idea of superconductivity, and it is irrelevant in the case of insulators because conductive temperature beyond melting point is not possible. Now, the relative ease at which electric current flows through a material is what is called conductivity. Conductors like copper have very high conductivity. Insulators have very low conductivity. The conductivity of a semiconductor depends on its conditions. For example, at low temperatures and low voltages, a semiconductor acts like an insulator. When the temperature and or the voltage is increased, the conductivity increases and the material acts more like a conductor. Metals are good conductors because a small percentage of electrons are free to separate from atoms and move independently. So, there is a large number of electrons that are free to move here. So, in case of conductors, it becomes easy to conduct electricity. So, many electrons are there which are free and they can move through the lattice. In case of non-metals, that is insulators, the electrons, they are tightly bonded to the atoms and cannot move. So, here these electrons, if you see the black colored, they are electrons, they are tightly bound with the atoms. So, as the electrons cannot move, they cannot carry current. So, there are no free electrons, you can say very small number of free electrons are present, electrons are trapped in the atoms and cannot move. And what about the semiconductors? There are a few electrons that are free and can move. So, electrons in a semiconductor, they are also bound with the atoms, but the bonds, they are relatively weak as compared to the insulators. The density of free electrons is what determines the conductivity of a semiconductor. Semiconductors are more like insulators in their pure form, but have smaller atomic band gaps. Adding dopants allows them to gain conductive properties. In the periodic table, this you can say group 4 is what is that of the semiconductors: carbon, silicon, germanium, lead and so on. If there are many free electrons to carry current, semiconductor will act like a conductor. If electrons are few, it will act like an insulator. In the case of semiconductors, silicon, as it is easily available, is the most commonly used. Atoms of silicon have 14 electrons. 10 electrons are bound tightly inside the atom and 4 electrons near the outside of the atom are loosely bound with the atom. Now, when you add foreign elements to the semiconductor, you can make it electropositive or electronegative, because semiconductor in the pure form shows conductivity only at large temperature, which you cannot increase after a certain value. So, we have to add some foreign element to the semiconductor, that is to the pure form of the semiconductor. which you call as intrinsic semiconductor, and we make this intrinsic semiconductor as extrinsic semiconductor. So, extrinsic semiconductor is that semiconductor in which we add impurity. To make p type semiconductor, the dopants that are included are boron, aluminum, gallium, indium and thallium. Like for example, if you dope silicon with boron, here is the boron boron atom. The boron atom will be involved in covalent bonds with 3 of the 4 neighboring silicon atoms, but the 4th bond will be missing, giving the atom what we call a hole. This hole can accept an electron. In the case of n type semiconductor, you can say negative type, dopants include nitrogen, phosphorus, arsenic, antimony and bismuth. Like for example, in the picture you are shown silicon which has been doped with phosphorus. Phosphorus has 5 electrons in its outermost orbit. So, 4 of the electrons they make covalent bonds, 5th electron is free. So, there is an excess negative charge in the case of this extrinsic semiconductor. So, we call it as negative type, that is n type semiconductor. So, majority carriers in n type is electrons, majority carriers in p type is holes. Then what is a transistor? So, it is a current driven device in which current in the emitter controls the current of the collector. How can you make a junction transistor? You have to grow a thin layer of one type of semiconductor in between 2 thick layers of other type of semiconductor. So, there are 2 types of transistors. If you grow a thin layer of n type between 2 p type thick layers, you get what is called a PNP transistor. So, a PNP transistor is obtained by growing a thin layer of n type semiconductor in between 2 p type semiconductor layers. So, this is the PNP transistor, this is its symbol. There is an arrow which is marked over the emitter. Arrow basically gives you the direction of conventional current, means from positive to negative, because emitter here is p type, positive type. So, and n means negative type. So, the direction of the arrow will be from emitter to the base. Second type of transistor is what is called NPN transistor. A NPN transistor is made by growing a thin layer of p type semiconductor in between 2 layers of n type semiconductor. So, there is a p type semiconductor here. So, this is a thin layer of p type which forms the base and 2 form what is called emitter and collector. Emitter is highly doped, collector is also highly doped, but lesser than emitter. Base is, you can say, very thin. As base is p type here, emitter is n type. So, direction of conventional current will be from p type to n type, that is from base to emitter. So, the thin layer is what is called base. This is lightly doped, and the other 2, as I told you, they are highly doped, emitter and the collector. Collector is moderately doped as compared to emitter. So, in the symbols, as we have discussed, the direction of arrowhead indicates the direction of flow of conventional current, that is from positive to negative. This is the symbol of NPN and this is the symbol of PNP. Here the arrow is moving inwards, here the arrow is moving outwards. So, you have to remember that if base is p type, emitter is n type, arrow will be moving outward, that is p to n. Now, as you see in the picture, this bipolar junction transistor, it consists of 3 adjacent regions of doped silicon, and each of this is connected to an external lead. The base is very thin slice of one type which is sandwiched by the complementary pair of the other type, hence the name we call it as bipolar. So, this is, you can see another picture of NPN and PNP transistors, emitter being heavily doped, base slightly doped, collector has moderate doping. So, if you want to write down the values, you can write down collector doping is usually 10 to the power 9, base doping is slightly higher 10 to the power 10 to 10 to the power 11, emitter doping is much higher, that is 10 to the power 17. So, this is how the bipolar junction transistor is constructed. This is the base region, this is very narrow, and this is a junction which is formed and we call it as emitter base junction. This is the collector base junction, this is the lead which shows the base, this lead goes for the emitter and the one coming out from the collector goes as the collector lead. So, this is how the control is there. Control is in the hands of the base. This is a picture like a, you can say that of a tap. So, base controls everything. If you see, this is a current flowing through it, emitter sends the current, base controls it and it moves over to the collector. So, force is what you call by voltage or current, water flow you can signify it with current, and this is how the amplification takes place. This is the physical structure of the bipolar junction transistor. So, there is a base region, emitter and collector. So, this is how basically it is constructed. These are practical bipolar junction transistors. This is the transistor, there is an emitter, base and the collector. This is the heat sink, so that the transistor does not get heated up. This is another picture of different kinds of bipolar junction transistors. Now, let us study the working of a transistor. This is a PNP transistor. Remember, emitter base junction is always forward biased. This is forward biased by this battery which has been named as VEB, that is voltage between emitter and the base. And remember that collector base junction is always reverse bias. Reverse bias means negative of the battery going to the positive, positive to the negative type, and forward biasing means positive to the P type, negative to the N type. So, here the battery is VCV. As emitter base junction is forward biased, the resistance of emitter base junction is low, and as collector base junction is reverse bias, resistance of collector base junction is high. So, in this case what happens is that this positive terminal of the battery, it repels the holes inside the P type emitter. The holes they are repelled from emitter towards the base. This gives rise to what we call as emitter current. Base is thin and lightly doped, so only 5% of them get neutralized into electron hole combination, which give rise to this base current. The rest of the 95% holes they pass over to the collector, giving rise to collector current. So, here emitter current is shown this way, this is the base current, this is the collector current. So, if you use Kirchhoff's law, then you can show that emitter current is basically equal to the sum of base current and collector current. Now, what happens is that immediately as one hole reaches the collector, it gets neutralized by an electron from negative terminal of the battery VCB. As soon as a hole gets neutralized with the electron, at the same time a covalent bond is broken in the emitter region. So, when the covalent bond is broken, the hole is repelled towards the base and the electron moves to the battery BEV. So, these directions that have been shown, they are of conventional current. So, the hole again moves over to the collector and an electron from VCV combines with this hole, neutralizes this hole. This is how the current flows. In the case of NPN transistor, if you see here, the terminals have been interchanged. Negative terminal going to the N type, positive terminal going to the P type. As we have discussed in PNP transistor, emitter base junction is always going to be forward biased. So, here emitter base junction has been forward biased by VEB. This is the battery that has been attached here. Collector base junction, it is always reverse biased by battery VCB, because here it has to take up the majority carriers and the majority carries the electrons here. So, electrons being majority carriers in N type, they get repelled by the battery. This negative terminal of the battery repels the electrons in this N type emitter. This gives rise to emitter current. As we discussed before also, base is lightly doped and thin. So, most of these electrons they pass through this base region to the collector region, and only 5% of these combine with the holes. These 5% electrons which combine with the holes, they give what is called base current, and then as soon as the electron reaches the collector, it flows to the positive terminal of the battery. As soon as an electron reaches the positive terminal of the battery, the covalent bond in the emitter side is broken, and so the electron from BEB enters into the emitter. So, this is how the electron flows in NPN transistor. Then this is the operation of a transistor. If you see, base controls the emitter current in the collector. There are three possible configurations of bipolar junction transistor. When we call biasing, we say emitter base junction is forward biased or collector base junction is reverse biased. Biasing means applying voltages to the transistor to achieve certain operating conditions. Applying proper voltages to the transistor to achieve certain operating conditions. If you use common base, means base is earthed, then inputs they are VEB and IE, output is VCV and IC. If you use common emitter configuration, input will be referred as BBE and IB, output will be referred as VCE and IC. If it is common collector configuration, input will be BBC and IB, output will be VEC and IE. Then what are common emitter characteristics? These are the graphs which are obtained between voltages and currents with emitter earth. Common emitter means emitter is earthed, emitter is common. So, when you obtain the graphs between voltage and currents with emitter earth, base as input terminal and collector as output terminal, because emitter has been earthed. So, input terminal is ought to be base and output terminal is the collector. This is the circuit diagram, in which if you see this emitter is earthed, and remember emitter base junction is to be forward biased. This is an NPN transistor that has been taken, base is P type. So, positive of the terminal battery terminal is to be attached to the base, negative of the battery terminal is to be attached to the emitter. We have to note down the current, as base current is small. So, a micrometer has been put in series, and there is a you can say voltmeter here, with which you can record the potential difference. Similarly, to record collector current, we use a millimeter, because collector current is large, and we use a voltmeter here to note down the voltage between collector and the emitter. Collector is N type. We are using an NPN transistor here, as collector is N type and collector emitter junction is to be reverse biased. So, positive of the battery is to be attached to the collector. There are three common emitter characteristics: input characteristics, output characteristics and transfer characteristics. Input means जो input ਦੇ ਉੱਤੇ ਚੀਜ਼ਾਂ ਹਨ, voltage or current. So, input characteristics, they are the graphs between base voltage and base current for different constant values of collector voltage. Then you can find the input resistance also. It is the ratio of small change in base voltage to small change in base current at constant collector voltage. The graphs, they will look like this. So, this is a graph between base emitter voltage and base current with collector emitter voltage constant. So, एक ग्राफ जो है वो एक वोल्टेज दे उत्ते है. This is at the first, this is for the second, and this second voltage is greater than the first one. Output characteristics, these are the graphs between collector voltage and collector current at different constant values of base current. So, here it is base current which is to be kept constant. The graph is between collector emitter voltage and collector current. The graphs will come out to be like this. This is another graph. This is the output characteristic, voltage, common emitter voltage and collector current, keeping base current constant. If you see, this lower one is at a lower voltage, and as the base current is increased, the graph shifts upwards. This shows the cutoff region, this is the saturation region. So, BJT has three regions of operation. One is called active. BJT acts like an amplifier here. This is the most commonly used portion of the characteristic. BJT acts like a short circuit in the saturation region. This is the saturation region, and then there is a cutoff region. This is the cutoff region. BJT acts like an open circuit, and when you use it between saturation and cutoff, it acts like a switch. There is a cutoff region, as we talked about, not enough voltage at base for the diode to turn on, no current flows from common collector to emitter, and the voltage at collector is VCC. Then there is a saturation region, voltage at the base exceeds 0.7 volts and the diode turn on, and the maximum amount of current flows from collector to emitter. Then there is a active region. These are again the graphs shown. This is the input characteristic and the output characteristic. The input characteristic looks like the characteristic of a forward biased diode. If you have studied the diodes, then this is just like a forward biased diode. Transfer characteristics, graphs between collector current and base current, keeping collector emitter voltage is what is called a transfer characteristic. अगर collector current और base current ਦੇ ਵਿਚਾਲੇ graph draw करिए, collector emitter ਦੀ voltage ਨੂੰ constant ਰੱਖਦੇ ਹੋਏ ਤਾਂ ਇੱਕ straight line ਬਣੇਗੀ, और इस characteristic ਨੂੰ ਅਸੀਂ transfer characteristic ਕਹਿੰਦੇ ਹਾਂ. Then we can find out the AC current gain. It is defined as the ratio of change in collector current to the change in base current at constant collector voltage. It is also called current transfer ratio. This is actual common emitter output characteristic that has been drawn, actually drawn. These are common base configurations as we talked, active regions, saturation region and cutoff regions. This is again common base characteristic, common emitter characteristics we have studied. Now, we study common base characteristics. This is not most commonly used configuration, but it is often helpful in the understanding of operation of the BJT. If you see, this is the collector current graph between collector base voltage and collector current. When we say common base, means base is common, base has been earthed. So, input terminal is emitter, output is collector. So, this is the output characteristic because it is between output quantities collector base voltage and collector current, keeping emitter current constant. So, here emitter current is constant, and if you see, this is the active region. This is the region which is used for amplification. This region is saturation region. Here you have the breakdown region, and below where emitter current is 0, we call it as the cutoff region. So, normally we do not use this cutoff and saturation region. This is used when we use transistor as a switch, and mostly used area is this active region. This is common collector BJT characteristics. If you keep collector common, means you earth the collector terminal common collector biasing circuit is basically equivalent to common emitter bias circuit, except instead of looking at collector current as a function of collector emitter voltage and base current, we are looking at emitter current. Here the current gain is 1. In the case of common collector, current gain is 1. So, that is why it is sometimes referred to as emitter followers. You can note it down in your notebook. We sometimes call common collector